Is Einstein's theory of light speed truly unbreakable? It's a question that has puzzled scientists and space enthusiasts for generations. The speed of light, a mind-boggling 299,792,458 meters per second, has long been considered the ultimate speed limit in our universe. Einstein's theory of special relativity, a cornerstone of modern physics, hinges on this fundamental constant. But what if we could push past this cosmic speed limit? Imagine a world where the laws of physics, as we know them, are rewritten. A world where interstellar travel, once relegated to the realm of science fiction, becomes a tangible reality. The implications of such a breakthrough are staggering, potentially reshaping our understanding of the cosmos and our place within it. The idea that nothing can travel faster than light has been a bedrock of scientific thought for over a century. It's a concept so deeply ingrained in our understanding of the universe that challenging it seems almost unthinkable. Yet, throughout history, science has proven time and again that our understanding of the universe is constantly evolving. Einstein himself, a revolutionary thinker who dared to challenge the scientific status quo, understood that scientific progress requires a willingness to question even our most cherished beliefs. His theories, while groundbreaking, were not meant to be static pronouncements but rather stepping stones on our journey to unravel the mysteries of the cosmos. Today, on the frontiers of scientific exploration, a new breed of pioneers is emerging, daring to ask the question, can we break the light speed barrier? These scientists are not seeking to disprove Einstein, but rather to build upon his legacy, pushing the boundaries of knowledge further than ever before. Their research delves into the strange and wonderful world of quantum mechanics, exploring exotic concepts like wormholes and warp drives. These theoretical constructs, once relegated to the realm of science fiction, are now being examined with renewed seriousness, fueled by tantalizing hints from the cutting edge of experimental physics. One of the key tenets of the theory of relativity is that as an object approaches the speed of light, its mass increases infinitely. This increase in mass means that an object would require an infinite amount of energy to actually reach the speed of light, making it physically impossible. To put it simply, imagine trying to push a car and make it go faster and faster. As the car speeds up, it requires more energy to accelerate it further. Now imagine that car's mass increasing exponentially as it approaches a certain speed. The energy required to push it even a tiny bit faster would become astronomical, eventually becoming infinite. That's the challenge posed by the speed of light. Our perception of space and time is a key factor in why we believe that breaking the speed of light appears unattainable. Einstein's theory proposed that space and time are not separate entities but are interwoven into a single fabric called spacetime. Imagine a trampoline as a representation of spacetime. A bowling ball placed in the center would create a dip, distorting the fabric around it. Similarly, massive objects in space like stars and planets create distortions in spacetime. Light, traveling through this fabric, follows these curves and bends, explaining why light from distant stars appears to bend around massive objects like our sun. This bending of light, known as gravitational lensing, is one of the many predictions of Einstein's theory that has been experimentally verified. The speed of light is not just about how fast light travels, it's a fundamental constant that governs the very workings of our universe. It dictates how energy and matter interact, how gravity works, and even how we perceive time itself. The idea that time is relative, another mind-blowing consequence of special relativity, is directly tied to the speed of light. Time slows down for objects moving at speeds close to the speed of light relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally verified using atomic clocks flown at high speeds. For over a century, Einstein's theory of relativity has stood as an unshakable pillar of modern physics, but even the most robust theories can develop cracks. In recent decades, a few intriguing anomalies and theoretical possibilities have emerged, implying that the speed of light barrier may not be as solid as we previously believed. These hints come not from attempts to disprove Einstein but rather from exploring the universe's deepest mysteries, delving into the bizarre realm of quantum mechanics and the mind-bending possibilities of spacetime manipulation. One of the most perplexing challenges to our classical understanding of speed limits comes from the world of quantum mechanics, where particles at the subatomic level exhibit strange and counterintuitive behaviors. In the quantum realm, particles don't behave like tiny billiard balls but rather exist in a haze of probabilities, their properties undefined until measured. This inherent uncertainty in the quantum world opens up possibilities that seem to defy the rigid principles of classical physics. One of the most bizarre phenomena in quantum mechanics is entanglement, where two particles become linked in such a way that they share the same fate, no matter how far apart they are. Imagine two coins flipped simultaneously, one landing on heads and the other on tails. This is a standard probabilistic outcome. Now imagine these two coins separated by vast distances, yet when one is observed to land on heads, the other instantly flips to tails, defying the limitations of distance and time. This spooky action at a distance, as Einstein famously called it, suggests that information might be transmitted between entangled particles instantaneously, regardless of the distance separating them. While this doesn't directly violate the speed of light, as no physical matter travels between the particles, it hints at a deeper interconnectedness in the universe that we are only beginning to understand. While quantum entanglement presents us with the possibility of instantaneous connections, other theoretical concepts propose ways to circumvent the speed of light by manipulating the very fabric of spacetime. Recall our trampoline analogy for spacetime. Instead of traveling through the fabric of spacetime, what if we could manipulate the fabric itself, creating shortcuts or warping it to our advantage? This is the fundamental idea behind the concept of warp drives, a staple of science fiction that has captured the imaginations of physicists and dreamers alike. By creating a region of contracted spacetime in front of a spacecraft and expanding spacetime behind it, a warp drive could, in theory, propel a spacecraft at speeds exceeding the speed of light without ever violating the laws of physics within its local spacetime bubble. Another intriguing theoretical concept that could potentially allow us to bypass the speed of light is the wormhole. Imagine spacetime as a folded piece of paper, with two distant points brought close together by a tunnel through the fold. This tunnel, a shortcut through the fabric of spacetime, is analogous to a wormhole. While still highly speculative, the mathematics of Einstein's general relativity allows for the possibility of wormholes. These cosmic shortcuts could, in theory, connect distant regions of the universe or even different points in time, enabling journeys that would take eons at subluminal speeds. However, creating and stabilizing a wormhole would likely require exotic matter with negative mass energy density, something that remains purely theoretical at this point. While the thought of spaceships zipping across the cosmos faster than light is captivating, let's take a step back and explore scenarios where exceeding the speed of light, at least in a sense, isn't entirely outlandish. Imagine pointing a laser pointer at the moon, a classic thought experiment. As you flick your wrist, the light spot from the laser appears to move across the lunar surface. Now, if you move your wrist quickly enough, that light spot can theoretically travel across the moon's surface faster than the speed of light. Does this mean we've broken the cosmic speed limit? Not really. What's moving faster than light here isn't any physical object or information, it's just the projected image of the laser. The photons themselves, those tiny packets of light, still travel from the laser pointer to the moon at their usual speed limit. Now let's turn our attention to the grandest stage imaginable, the universe itself. In the first fleeting fractions of a second after the Big Bang, according to the theory of cosmic inflation, the universe underwent an exponential expansion, growing from a size smaller than an atom to a mind-bogglingly vast expanse in the blink of an eye. This rapid expansion, far exceeding the speed of light, is not considered a violation of relativity because it involved the stretching of space itself rather than the movement of objects through space. Think of a balloon with dots drawn on its surface. As you inflate the balloon, the dots move farther apart, not because they're moving across the surface, but because the surface itself is expanding. Similarly, during cosmic inflation, galaxies weren't moving through space faster than light. Space itself was expanding, carrying the galaxies along with it. While the exact mechanisms driving cosmic inflation are still under investigation, it serves as a compelling example of how superluminal expansion can occur within the framework of Einstein's theories. Returning to the realm of the very small, quantum mechanics offers another intriguing phenomenon that seems to defy classical notions of speed and barriers: quantum tunneling. Imagine a particle trapped inside a box. Its energy insufficient to overcome the walls confining it. Classically, this particle would be stuck, but in the quantum world, there's a chance it can spontaneously tunnel through the barrier, appearing on the other side as if it had found a shortcut through a hidden dimension. This tunneling effect is not about the particle traveling faster than light through the barrier. It's about the probabilistic nature of quantum mechanics, allowing it to exist on the other side without ever physically traversing the space in between. It's as if the particle took an instantaneous sidestep, bypassing the barrier altogether. Quantum tunneling plays a crucial role in various physical phenomena, including nuclear fusion in stars and the operation of transistors in our electronic devices. Finally, let's delve into the strange world of the quantum vacuum. Far from being empty, the vacuum of space is teeming with virtual particles, constantly popping in and out of existence, their presence fleeting but measurable. This quantum foam, as it's often called, gives rise to a curious phenomenon known as the Casimir effect, where two closely placed, uncharged metallic plates experience an attractive force, seemingly pushing them together. This force arises from the difference in the wavelengths of virtual particles that can exist between the plates compared to the wavelengths of those outside. This difference in energy density creates a pressure imbalance, effectively pushing the plates together. While the Casimir effect doesn't directly involve superluminal speeds, it highlights the bizarre and powerful consequences of quantum fluctuations in the vacuum, suggesting that space itself is far from passive and can exert forces that influence the motion of objects. The implications of breaking the light-speed barrier are nothing short of astronomical, fundamentally changing our understanding of the universe and our place within it. If we could somehow circumvent this cosmic speed limit, the universe would transform from a vast and seemingly impassable gulf into a more interconnected and accessible playground for exploration. Imagine reaching distant star systems, once considered unreachable within a human lifetime, and unlocking the secrets held within alien galaxies. The vast distances that currently separate us from these cosmic wonders would shrink, making interstellar travel and communication a tangible reality rather than a science fiction fantasy. We could witness the birth of stars in distant nebulae, study the atmospheres of exoplanets in search of life, and perhaps even make contact with other intelligent civilizations that might grace the cosmos. Breaking the light-speed barrier would usher in a new era of cosmic exploration, expanding our horizons beyond our wildest dreams. Beyond the promising prospects of interstellar travel, surpassing the speed of light would revolutionize our understanding of the universe's fundamental forces and the nature of space-time itself. If we could send information faster than light, it would challenge our current understanding of causality, the relationship between cause and effect. Events that we perceive as happening in a specific order might appear differently from other perspectives, blurring the lines of past, present, and future. Such a paradigm shift would force us to rethink our models of the universe, potentially leading to the unification of seemingly disparate theories like general relativity and quantum mechanics. Perhaps a deeper, more fundamental theory awaits discovery, one that encompasses the bizarre world of quantum entanglement and the mind-bending possibilities of space-time manipulation within the framework of a universe where the speed of light is no longer an unbreachable barrier. Time travel. Perhaps the most captivating implication of breaking the light-speed barrier is the possibility of time travel, a concept that has fascinated humanity for centuries. Einstein's theories of relativity suggest that time is not absolute but is relative to the observer's frame of reference, and that time slows down for objects approaching the speed of light. If we could exceed this speed, could we potentially turn back the cosmic clock and journey into the past? While the idea of altering the past is fraught with paradoxes and philosophical dilemmas, the theoretical framework for time travel does exist within the realm of Einstein's equations. Wormholes, theoretical tunnels through space-time, could potentially connect different points in time, offering shortcuts through the fabric of the universe. However, the stability and controllability of such wormholes, and the very possibility of surviving a journey through them, remain open questions, firmly in the realm of speculation. The quest to break the light-speed barrier is not merely about satisfying our thirst for speed or achieving technological marvels. It's about pushing the boundaries of human knowledge and understanding our place in the cosmos. Whether or not we can truly surpass this cosmic speed limit remains to be seen, but the pursuit itself is a testament to the power of human curiosity and our relentless drive to explore the universe's deepest mysteries. As we delve deeper into the bizarre realm of quantum mechanics, explore the mind-bending possibilities of space-time manipulation, and continue to test the limits of Einstein's theories, we embark on a journey of discovery that promises to reshape our understanding of the universe and redefine what's possible. The speed of light, once considered an unbreakable barrier, might one day become a stepping stone to a future where the universe's most distant reaches are within our grasp. As we've journeyed from the heart of atoms to the edges of the observable universe, one thing has become abundantly clear. The quest to break the speed of light is not just about speed itself, it's about pushing the boundaries of our understanding, questioning our assumptions, and embracing the sheer wonder of the cosmos. The pursuit of knowledge thrives on challenges, on daring to imagine a reality beyond our current grasp. Einstein's theory of relativity, a cornerstone of modern physics, has withstood the test of time, but as with any scientific theory, it's not immune to questioning and refinement. The anomalies we've explored, the promising hints of faster-than-light phenomena, and the theoretical possibilities that dance at the edges of our understanding remind us that science is a journey, not a destination. The universe holds countless secrets, and the pursuit of those secrets fuels our desire to explore the unknown. So is Einstein's theory of light speed truly unbreakable? For now it remains a cornerstone of our understanding, yet the universe is full of surprises. Perhaps hidden within the fabric of space-time or in the bizarre realm of quantum mechanics, lie the keys to unlocking a new era of cosmic exploration. An era where the speed of light is no longer the ultimate barrier, but a stepping stone to a more interconnected and awe-inspiring universe. Thank you for joining me on this journey through the frontiers of physics and the tantalizing possibilities that lie beyond the speed of light. What are your thoughts on these mind-bending concepts? Do you think we'll ever break this cosmic speed limit? Share your thoughts and questions in the comments below.